Well, hi everyone, this is Bob the Science Guy. We're getting ready to finish off Chapter 1 of University Physics 2. The final section is heat transfer, specific heat, and calorimetry. This is actually one of the more interesting sections in this chapter. Now, in the first section, we talked about thermal equilibrium. In other words, if you put something hot next to something cold, heat will go from the hot object to the cold object to the point that they are both the same temperature and are in thermal equilibrium. Now in this example from the book, we have a warm soda can at say 15 or 20 degrees Celsius, and we have an ice cube. And if this is an isolated and insulated system, heat from this soda can will travel to the ice cube. And because they're separated by a distance, that heat will travel via convection. In other words, the soda can will warm up the air, which in turn will warm up the ice cube, and by radiant heat. So the small amount of infrared coming off of this warm soda can will travel over to the ice cube and heat it up. In the situation here, we have the first two forms of heat transfer, but now we also have conductive heat because they're in direct contact with each other. Now the unit of heat is the calorie, and that is the amount of energy from heat required to raise the temperature of 1 gram of water 1 degree Celsius. A kilocalorie is the amount of heat required to raise 1,000 grams of water 1 degree Celsius. And 1 calorie has got a mechanical equivalent of 4.2 joules. Now, whenever you're doing a process that involves transferring heat, be it distilling whiskey or making steel, it's a good idea to be able to figure out how much fuel you need to use in order to accomplish the job. You don't necessarily want to buy too much fuel because that becomes expensive, but you want to make sure that you have enough to do the job. So one of the questions that came up is, what is something called the heat capacity of a substance? So the heat capacity of liquid water, for example, is 1 calorie per gram per degree Celsius. Well, how much heat does it actually take to change the temperature of water? Well, let's go ahead and look at first the latent heat of water. Now in SI units, that's 4186 joules per kilogram. It's also 1 kilocalorie per kilogram of liquid water, or 1,000 calories per kilogram of liquid water, because a kilogram, of course, is 1,000 grams. So here's the formula. The heat is going to be the mass times the heat capacity times the temperature change. So if we have 10 kilograms of liquid water, we're going to multiply that times, I don't know, let's do it kilocalories per kilogram, times the change in temperature, which is 20 degrees, and that should be pretty simple to figure out. It's 200 kilocalories. That is the amount of energy or heat required to raise the temperature of 10 kilograms of water 20 degrees Celsius. Well, what happens when you're dealing with two different substances? There's a great example in the book, and let's go over it right now. So we've got a 0.5 kilogram aluminum pan and 250 mils of water, and we heat both of them from 20 to 80 degrees Celsius. Now, how much of a temperature change is this? It's obviously 60 degrees Celsius. That's the difference between the ending temperature, 80, minus the beginning temperature, 20, 60 degrees Celsius. Now, the mass of the water is 0.25 kilograms. Using the specific heat of water, what we're going to do to figure out the amount of heat required to raise the temperature of the water 60 degrees, we're going to take the mass of the water times the specific heat of the water times the delta T. So the mass of the water is 0.25 kilograms. The specific heat of the water is 4186 joules per kilogram, and the delta T is 60. So we've got 62.8 kilojoules. Now we're going to do the exact same thing with the aluminum. So once again, the mass of the aluminum is 0.5 kilograms. The specific heat of aluminum is 900 joules per kilogram per degree Celsius, and it's 60 degrees Celsius is the delta T. So it's 27.0 kilojoules. Add the two together, we get 89.8 kilojoules. So the interesting thing from this problem is even though the aluminum pan is much heavier than the water, its specific heat is considerably lower, on the order of 1/4. And as a result of that, only about 1/3 of the total heat required is used to heat the aluminum pan, whereas 2/3 of the heat is heating the water. So here's an interesting problem from the book. We have a 10,000 kilogram truck on top of a hill. It goes down the hill with a total vertical drop of 75 meters. And we want to know the resulting temperature in the brakes. Well, first of all, we have to figure out how much energy is being spent here. What's the loss in potential energy? Well, it's 10,000 kilograms times 75 meters times 9.8 meters per second squared. So about 7,350,000 joules. Now, because the speed of the truck doesn't increase, the kinetic energy is not increasing. So this loss has to go into heat. Now, according to the problem, the brake pads weigh 10 kilograms and they absorb 10% of the heat. The other 90% of the heat is presumably lost to the atmosphere. So we want to know the resulting temperature change of the brakes. Well, let's look back up here at our problem. The heat energy, Q, is in joules. The mass is in kilograms. The heat capacity of the brake material is in joules per kilogram, and it is listed as 800 joules per kilogram. Okay? And we want to solve for the change in temperature. Well, we can just come down here and rearrange this a little bit. Let's go ahead and take Q. We're going to divide it by MC, and that will equal delta T. Pretty straightforward. So what is 10% of 7.35 times 10 to the 6 joules? Well, we basically divide it by 10, and that would give us 7.35 times 10 to the 5th joules. So we're going to go ahead and put that right here. And what are we going to divide it by? Well, the mass of the brakes is 10 kilograms. The heat capacity of the brakes is 800 joules per kilogram. So we'll multiply that right here. So what are we going to end up with? This will end up giving us temperature in degrees Celsius. So let's just go ahead and do the math. Okay, and there we have it. So it comes up to 91.875 degrees. And that is actually the answer that's in the book. Now let's look at one more concept, and that is phase changes. Now, for example, let's consider the problem of boiling an ice cube. Let's see how much energy it would take to take 100 grams of ice and make 100 grams of steam out of it. We have to melt the ice to water, and then we need to boil the water to steam. So let's look at that real quick. So every good math problem starts with a diagram, and so let's draw a diagram here. So we've got 100 grams of ice. We're going to have to apply some heat to melt that ice. We're then going to have to heat the water up, and then once it gets to 100, we have to boil that water off to steam. Now we know already to heat liquid water, it's 1 calorie per gram. But how much heat does it take to melt a gram of ice to a gram of water? As it turns out, it's 80 calories per gram. We have 100 times 80 equals 8,000 calories. Okay, so now we've converted 100 grams of ice to 100 grams of water. They're all still at 0 degrees Celsius. Now we need to raise that water from 0 degrees Celsius to 100 degrees Celsius. That's going to be 100 grams of water times 100 degrees is going to be 10,000 calories. So now we've got liquid water at 100 degrees. Now we need to convert that 100 degree water to 100 degree steam. And that's going to take 540 calories per gram. So that's 100 grams of water times 540 equals 54,000 calories. So for our grand total, we've got 72,000 calories. That's how much it will take to do this whole operation. Now, when we boiled the ice cube, we had an unlimited amount of heat. and all we needed to do was calculate how much heat would be needed to boil the ice cube to steam. Sometimes we just have a limited amount of heat and we need to find the resulting temperature. Now, a classic example of this is a glass of water with an ice cube in it. So say that the water starts off at 15 degrees Celsius and the ice cube starts off at 0 degrees Celsius. Say we have 100 grams of water and we have 50 grams of ice. What is the resulting temperature of the solution? Well, let's go ahead and work through that real quick. So here's the basic idea. So the amount of heat energy lost by the water equals the amount of heat energy gained by the ice. And as a result, the net is 0 because energy is neither created nor destroyed. That also means that the Q of the water equals the negative Q of the ice. Whatever this side loses, that side gains. So we said that we had 100 grams of water at 15 degrees Celsius. So how many calories do we have here? So we have 1,500 calories in the water. And then we said that we had 50 grams of ice at 0 degrees Celsius. The first question that we should ask ourselves is how much heat is required to melt 50 grams of ice? Well, we said that the melting heat of ice is 80 calories per gram. So that would be 50 times 80. That equals 4,000. So the bottom line is we do not have enough heat available from the water to melt the ice. So by the time we're in thermal equilibrium, we're going to lose 1,500 calories from the water. We're going to gain 1,500 calories with the ice. And the resulting solution will be a solution of water and ice at 0 degrees. Now the next interesting question. We had 1,500 calories worth of heat energy to work with. We're not going to have 50 grams of ice left. Some of it's going to melt. Well, how much of it will melt? So we have 1,500 calories. It takes 80 calories per gram to melt ice. Looks like we had enough heat energy to melt 18.75 grams of ice. But what if we have a situation where we have far more heat than is required to melt the ice? So let's take 1 liter or 1,000 cc's of boiling tea at 100 degrees Celsius. So we got 1,000 grams of water. The heat capacity of water is 1 calorie per gram. And the temperature is 100. So we're dealing with 100,000 calories. Okay. How much will it take to melt 50 grams of ice? Well, that's 50 times 80 equals 4,000. So we have much more than is required to melt this ice. Well, what's the resulting temperature of the iced tea after this melts? Well, the way that we're going to do that, temperature final equals the number of calories in the water minus the number of calories required to melt the ice over the mass of the water and the mass of the ice. Let's go see what that comes out to. So that's 96,000 divided by 1,050 is 91.42 degrees Celsius. It's certainly not enough. This is not enough ice to cool that amount of tea. Now there's some pretty elaborate formulas in the book for coming up with a final temperature. Probably the easiest way to do that is figure out how much heat you need to get both sides of the equation into the same phase. So in other words, how much heat would you need to melt the ice to make the ice liquid and the soda liquid? And then use the available heat left to come up with a final temperature. So that's pretty much it for chapter 1. I may do one more just for completeness, but I think that pretty much covers most of it. Good luck on the quizzes, and I'll see you again soon. Take care.